Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced these useful number systems that you're going to be using throughout this linear algebra portion of the course as well as the calculus portion of the course that you may have already seen before. So that was the natural numbers, the integers, the rational numbers and the reals. And as well as that we introduced this kind of unique set that I said, which was the empty set. And in kind of towards the end of the video I talked about some special subsets, I use this word subsets, of the real numbers, and those were kind of intervals of the real numbers. And in this video what I want to do is I want to explore what a rigorous definition is of it means to say that something is a subset of something else. So if a set is a subset of another set. And using that we're going to construct an idea of equality. We want to construct a rigorous definition of equality of sets that captures some of these ideas that we said in our first video about our intuitive idea of a set. So recall that we said that if we had a set with some elements in it, we had this kind of bag with 3 coloured balls in, and we shifted around the order that those balls appeared, that those two sets should be equal, right? That it should be the same. The first set with the balls in that configuration should be equal to the second set with the balls in this new configuration. So let's move to our first definition. And our first definition is going to be that of a subset. So in this case, what we're going to do is we're going to take two sets and we're going to call them S and T. Now, if every element of S is also an element of T, then we say that S is a subset of T. So this is just effectively how will we check that? We look at all the elements of S and we check that all those elements are also in T, and then we would say S is a subset of T, as you might expect. And we have a special type of notation for that. So if S indeed is a subset of T, we kind of write this S with a U on its side, T, to mean S is a subset of T. And much like we have this kind of universal notation when we want to negate that, generally what we do is we draw a line through things. If S is not a subset of T, if we know explicitly that S is not a subset, then we write S with its U on the side and a line through T. So that's the notation we use to describe whether or not things are subsets or not subsets. So let's look at some examples of things that are subsets. Well, the first one I want to consider here is I've got two sets that I've just got A and B. A is the set consisting of the elements 1, 2, and 3, and B is the set consisting of the elements 1 and 2. So let's go through all these elements and check which sets they both belong to. So clearly if I take the element 1, 1 is both in B and in A. And indeed also 2 is also an element of A and B. So in other words, we've deduced here now that all the elements of B are also in A. So B is a subset of A, right? So we can write that B is a subset of A as all the elements of B are in A. What about the other way around? Well, all the elements of A are not in B because the element 3 is in A, but it's not in B. So in fact, A is not a subset of B. So let's consider another example here. So we've got A is the set of capital cities on Earth, and B is the set of cities on Earth. So A is the capital cities, which is more restricted than the set of cities. So it must follow that A is a subset of B, because every capital city, by definition, is a city. So we write A is a subset of B. But similarly like to before, B is not a subset of A, because there are examples of cities on Earth that are not capital cities. For example, Nottingham is a city, but it is not a capital city. So let's consider our third example. So we consider our number systems from the previous video, and it follows by their definition and almost by their construction that they're each subsets of each other, kind of going up the chain of command of which ones are larger than the others. So that is to say that the naturals are a subset of the integers are a subset of the rationals are a subset of the reals. And actually, if I go in the reverse direction, it's fairly clear that they're each not subsets of each other. That is to say that the reals are not subsets of the rationals are not subsets of the integers, and the integers are not subsets of the naturals. And that just follows by just considering how we constructed these things, right? That I can find an irrational number in the reals and therefore it's not in the rationals. I can find a fraction, say like a half, that is not an integer, and I can find a negative number or 0 that is not a natural number. So it's fairly easy to see this kind of chain of command of the number systems that we have. So the next thing to consider is using this idea of subsets, this definition of subsets. Can we construct a definition of equality that captures this idea that we said kind of in the first video about how sets, the kind of ordering in which objects appear within those sets, doesn't matter. So Let's write down our definition of equality. And here, as before, we're going to take two sets S and T. And we'll say that if the set S is a subset of T and T is also a subset of S, then S is equal to T. So that's what we mean when we say S is equal to T. In other words, all the elements of S are also in T and all the elements of T are also in S. And we use the notation that, as you might expect, that if S is indeed equal to T, we just use the notation S is equal to T. So this is actually the kind of rigorous notion of what we mean to say whether or not two sets are equal. So all the elements of S are in T and all the elements of T are in S. And you might say, okay, that's fairly obvious and that's fairly simple, but let's look at a couple of examples and see that some of them are not entirely trivial. The first one we've got here, we want to capture this idea of the order not mattering. So we've got here A is the set containing the elements 1, 2, and 3. And B is the set containing the elements 3, 1, and 2. Well, A and B are clearly equal because all the elements of A appear in B and all the elements of B appear in A. And we see that as well that B is just kind of a reordering of the elements of A. So in our definition, we've come round in circles now and said indeed that A equals B. So this is exactly a reasonable definition of equals, because our kind of initial example where we took the balls again, the coloured balls in the bag, and we kind of shifted them around in a different order, those two sets are now equal according to this definition that we've constructed here. And this gives us this idea, or why we use this word in set theory, that it's a collection of unordered elements. The order doesn't matter, at least at the level of set theory here. So what's our next example? Our next example I want to consider here is set T, and this is the set of elements that X that are integers. And we also have the condition that x squared equals 2. Now, indeed, you can find a number for which x squared equals 2, for example, the square root of 2, but unfortunately, I'm also restricted here to x being an integer. And the square root of 2 is not an integer. So in fact, there are no elements in this set that satisfy the conditions, and therefore it's the empty set, right? Because the set contains nothing, that contains no elements, and I already said that the empty set was unique, hence T must equal the empty set. So that's kind of a bit of a trickier example to think about. But the third one here is kind of a bit mind-boggling, but is indeed true thinking about our definition of equals. So here we take A is the set containing the elements 1 and 0. And B is the set containing 2 copies of a 0 and 3 copies of 1. Now, are these sets equal? You would say, okay, clearly they're not equal because there's different numbers of elements in both sets. But let's go to our definition. Go through all the elements in the set A and check that they're in B. So the element 0 is in A and it's also in B. The element 1 is in A and it's also in B. And let's check all the elements of B. Well, the only other elements in B are again 0 and 1. So all the elements of B are in A. So it follows that A is a subset of B, B is a subset of A, and therefore A equals B. So this seems a bit odd. We've got two sets here that initially we say, oh, well, they're clearly not equal because they've got different numbers of elements, but in fact they are equal according to our definition. In fact, these two sets actually have the same number of elements because this is the way in which we count things in, at least in set theory, that we can only count distinct elements. And here we've only got 2 distinct elements, that is 0 and 1. But we're not going into too much kind of rigorous detail about how we construct these counting systems or how we construct the number of elements in sets that is otherwise referred to as the cardinality of sets. So we're not going to go into these technical details within this course, but that's just kind of an idea here where you can see that it's a little strange that these two sets appear to be non-equal, but according to our definition are perfectly valid to be equal. So that's where we're going to conclude the video now. And in the next video, we're going to continue looking at some kind of more structures on set theory. And again, within the context of set theory, and I should say again, I reiterate, can you please look at the notes on the Moodle page as well as answer any questions in the module handbook related to this video. So I'll see you in the next video, and thanks very much for watching.